electrocute some complete strangers. I'm off to the circus. And Jem is going to build and ride a toffee rocket. That's Bango's the theory, putting science to the test.
Off, we thought we'd let Jem here loose in his workshop again.
He's only gone and built a rocket. Welcome to Britain's newest space centre, the Bango's the Theory rocket test base at the Buckinghamshire Railway Centre. When you think spaceflight, think NASA, Apollo, space shuttles and a couple of billion quid to burn. But there's a new game in town. Gone are NASA's billion-dollar rockets. The future is from the supermarket. Toffee-powered rockets built for peanuts. I'm going to build myself a rocket bike, and I have a sneaking suspicion it's going to be the cheapest manned rocket mission ever. Apollo-style rockets were hideously complex, but hybrid rockets just require a cheap solid that burns, and a gas to provide oxygen. And that will make it burn more fierce. The power of a rocket is largely dependent on the calorific value of the fuel. And there aren't many things with a higher calorific value than toffee. So a burnable solid and an oxidizing gas make a ferocious flame. And that's what fuels a hybrid rocket. Hybrid rockets aren't just cheap and cheerful, they're relatively safe too. Old liquid rockets wanted to blow up as soon as you looked at them, and solid fuel rockets, like fireworks, once lit can never be stopped. The idea of a hybrid rocket is really simple. Given enough oxygen, almost anything will burn, even this plastic tube. All I need to do is fire a gas down the middle and ignite the walls of the tube itself, so it becomes the fuel. And that is the essence of a hybrid rocket. A huge safety advantage of hybrids is their controllability. It might be 2,500 degrees in there, but as soon as you shut off the oxygen supply, the thrust drops right off. Great, but you still have to treat them with an enormous amount of respect. This bit of 2-inch diameter steel water pipe is what's going to be the main body of my rocket. This is where it's going to have the highest pressure, and it's just about good for that. Now, in the centre of this, it's going to be cast a whole load of toffee. Now that toffee is going to have a hole right down the middle of it, and the purpose of that hole is so that I can fire high pressure nitrous oxide gas in there. That means when the toffee's set alight, the entire internal surface of that hole can start burning, gets to a phenomenal temperature, and the internal pressure of this gets very, very high indeed. You might not think toffee is a rocket fuel, but burn it with high pressure nitrous oxide, laughing gas to you and me, and it's pretty impressive. After just 10 seconds of burn, pressure was too much for the steel. The weak point is just exactly there at the throat of the nozzle, just hosing out plasma everywhere. I can't sit on a bike with that behind me. The burn through always happened at the narrowest part of the nozzle, and after a few experiments, I had a design that I hoped would hold together just long enough. I was ready to risk my life. Old fire extinguisher, full of nitrous oxide. Release valve, operated by brake lever. Plumbing pipe, filled with toffee. Burnt and accelerated through here at Mach 5. What could possibly go wrong? Three, two, 1, ignition. Don't explode, don't explode, don't explode. Oh, that was incredible. Toffee makes amazing rocket fuel. But I think we can still cook up something better.
Jem, you're seriously nuts. That was madness.
Don't tell me you were not scared.
I was petrified. Okay, now toffee's great,
Yeah.
but I want more calories. So I'm moving on to peanuts. These little fellas here are packed with fat, and I think I'm upping the burn
making a
temperature. No, I'm not, honestly. The extra fat in the peanuts lifts the burn temperature more thrust.
Seriously?
Yeah, and even more thrust, a little bit of aluminium powder.
Aluminium, okay, hold on a second. What does that do?
Well, it doesn't taste great. Oh, but this stuff burns. Once you get the nitrous through the aluminium powder, you're really getting something special. But Dallas, don't worry about the little fella.
Okay, I won't.
Because we've moved on to this.
Oh, look at that.
That's
magnificent.
incredible.
This fella is going to give 250 kilos of
You're
thrust.
mad. You're completely mad.
Rockety.
That's not even a word. Find out what happens with the beast later on in the show, but for now, it's time to catch up with Dr. Yan.
Using just this battery and this bit of wire, I'm going to stick these two bits of metal together so firmly that I can hang from the ceiling using them. Well, that's the theory anyway. The way I'm going to do it is to use magnetism. Now, I'm sure you've all seen magnets before, but these lumps of iron are definitely not magnets. They don't pick up things in the same way magnets do. Do you want to give it a try? Tell me if they stick together. No. Okay, cool. It's not a magnet now, but I can turn it into one. In fact, a very strong one with just a little bit of electricity. If I take a wire and run an electric current down it, then it will become a little bit magnetic. And if I coil it round and round, it will act a bit like one of these magnets. It's called an electromagnet. To make a really strong magnet, I don't necessarily need much current. If I coil the wire a lot, then I'm bringing the same current round and round, building up more magnetic field with each turn. And if I coil it round this iron, then it can get even stronger because it's easier to build up a magnetic field in iron than it is in air. I'm hoping that way I can make it strong enough. This actually illustrates one of the most fundamental laws of the universe. When you have electric charges, that's what an electric current is, that are moving, they generate a magnetic field. And also, if you have magnets moving, they can generate an electric current. And actually that's how nearly all of our electricity is made, by turbines moving magnets around. Right. I think I would quite like a volunteer. You put your hand up first. What I'm going to do is I'm going to ask you to stick a battery onto that, yeah? And then when I say go, you're going to take the battery off by pulling that. Does someone want to clip that to the little thing on my back? Okay. Where's it gone? There it is. Okay, so put the battery in. Yeah, that feels like it's pretty strong. Right. Oh, remove the ladder. Right. Here we go. Way! I seem to be being held up okay. Now, it's obviously holding my weight. Okay, do you want to undo it now? It worked. Very good.
Oh, I love Jan's films.
I know, they work for me.
They're full of sciencey goodness. Speaking of sciencey goodness, keep your questions coming in to Dr. Yan. Thomas from Bristol's got a really good one. Why do we dream? I had a weird dream last
I
night.
so don't want to know about that
I'll
one.
tell you later.
Now I'm scared. If you want to know the answers to that question and all the other questions we are posing our resident brain box, of course, do check out our website, which is, of course, /bang.
Yeah, and of course you can take the Bang Interactive Science Challenge. Just follow the links to the Open University.
Jan used a coil of wire to make an electromagnet strong enough to hold his own weight. Electric motors use this same magnetic effect to produce their turning force, and because it all happens literally At the flick of a switch, you get full force straight away.
And I'm going to demonstrate that using a winch, a 4x4, and my mate Andy here. Take it away, Andy.
Yours has bravely volunteered to demonstrate all of this.
It's the electric current flowing through the coils of wire in those motors that's providing the magnetic field whose invisible push and pull creates all the force necessary to lift the whole thing skyward.
Yeah, now those motors are part of that winch, and that winch is attached to our crane and gantry up there, and it's almost up at the top now.
I'm basically entrusting my entire life on that fantastic little bit of science.
I'm not sure I would have done that.
Okay, now that we've proven this point, time for me to do some little experiments on our sense of smell. Many animals have an amazing sense of smell, and by comparison, we tend to think that as humans are pretty rubbish. But actually, we're not as bad as we think. In fact, I reckon I can make the visitors here tell the difference between virtually identical smells. Would you like to help us out with a little... So, I need to find some willing volunteers. I'm going to give you two smells. Okay, so this is green. Initially, they find it hard to tell which of the two similar smells is which. Green. Red. Really? Yeah. Wrong! I'm not going to tell you whether you got it right or wrong. So, can I improve our punter's performance? It's a component now. You don't have a pacemaker or any heart problems or anything, do you? Okay, we do the whole thing again, but while they sniff one of the smells, I give them something to remember it by. This? An electric shock. Okay, you smell green. This is red. Ooh. Oh. Is it wrong that I'm enjoying this so much? So, has that little jolt helped them to recognise the difference between the smells any better? Now, which one is this? Could be green. We have a result. It is red! Guess what? It's red! Thanks a million, guys. We have a result, people. Good man. It works because smell, emotion, and memory are directly connected by neuronal pathways in our brains, and because of that, they can easily enhance each other. The human sense of smell can distinguish between billions and billions of different types of smell, and that's because our brains are wired for smell. In fact, why don't I show you? With a little help from a friendly surgeon, Mr. Janon, we're going to poke this little camera up my nose.
Just relax. Just relax your shoulders. Okay. This camera's going to go.
Up here somewhere is the closest I'm going to get to my brain.
So, on this side, what you can see is what's called the septum, which is the bone that divides the nose into two halves.
Right.
And this is the roof of the nose. And if you can see, there's a slight colour change.
Okay.
It's pink here, and it's just slightly yellow just at the top there.
These are my olfactory neurons, or smell receptor cells. And essentially, they're an extension of the brain because they connect directly through the skull and into my grey matter. So our sense of smell is literally hardwired to our brain.
That's right, Liz.
Ooh. Thanks, Doc. So can we use this connection to make us smarter? The smell of school brings me right back to my childhood. And you know, we've all been there when a certain smell triggers a really strong memory. Well, some students here at Burley Community College in Sheffield are making brilliant use of that very fact. They've designed these ingenious scented pen tops, revision aids which they claim can improve your exam marks using only the sense of smell. So guys, tell me first of all how all this came about.
We did a bit of research and we asked lots of people what they thought about exams, and most of them said they get stressed.
There were a newspaper article on it saying that smell triggers your memory.
We brought that into context with teenagers with exams.
How did you go about designing these things to stick on the pens then?
We all went off and designed one ourselves, so...
Right.
It would have to be something that were small, that you could put in your bag so that you're not going to forget.
I have to tell you, I am really, really impressed with you all. Congratulations. Time to put it to the test. Miss Dolan's Year 7 class have memorised a group of objects while sniffing a lemon smell. Today we're going to see how many of the 25 objects they can remember. All the children get a smelling aid for the memory test. Half of them are given the lemon smell that they revised with, but the other half receive a different smell, strawberry.
So, are we ready? Fantastic. Lids off, pens then.
If it works, those with the right smell, the yellow pen tops, should score better than those with the red pen tops.
Okay, you've got 1 minute left. Okay, Year 7, if you could put your pens down now, please.
Are you ready? Are you nervous? I can tell you that the red team, the ones who had the pens with a different smell, got an average score of 14.5, which isn't bad at all. So well done, you guys. And now the moment of truth. You guys got an average score of 17, which means you won! Congratulations! Just goes to show the power of smell is nothing to be sniffed at.
So them doing that experiment, it's a really interesting thing how smell and memory is connected, isn't it?
Yeah, we've all had that connection, haven't we, at some point? Mine is popcorn. It always takes me back to being a kid.
Interesting.
Yeah. Jem, what is this?
This is supposed to be a perpetual motion machine. This is a classic perpetual motion machine design. And the idea is, if you spin it in the right direction, it keeps on going forever.
I need to spin it, obviously. Which direction? Does it matter?
This way.
Okay.
What's happening is the weights slide out further on this side and then get pulled in on this side. There it gives more weight there and it keeps on going.
The problem is, it doesn't work, does it?
No, it simply doesn't work, and that's because the only energy you put into this was the push that you gave it.
You're calling me a weakling?
No, it was a good push.
Thanks.
But then that energy gets absorbed, it gets used up, converted into like heat in the bearings, you get the friction, knocking here, more heat. Once that energy is all used up, the wheel stops.
Okay, so perpetual motion machines simply don't work then?
No, they never work.
Oh.
They never will work. That's the thing about energy. Energy isn't made, it's simply converted from one form to another. So for example, you've got chemical energy that's locked up in coal, and that may heat water. You heat the water, which generates steam. The steam expands and will drive a piston. You've got a steam engine.
And so on and so on. And the coal comes from plants that are compressed over millions of years. Plants get their energy from the sun. But where does the sun get its energy from?
Indeed, Liz, that is the badger. I have to refer to Einstein's famous equation here, E equals mc squared, where E stands for energy, M is mass, it's like substance, things, and C is the speed of light. So C squared is just a massive number. And what it's saying is energy is actually equal to mass multiplied by a huge number. Energy and mass are interchangeable. But the thing is, a small amount of mass gets converted into a vast amount of energy. For example, 1 kilo of mass could theoretically be converted into enough energy to run a city of 2 million people for 2 months.
Exactly, and that essentially is how the sun works. So if the sun can do it, why can't we do that here on Earth? I went to find out. What you're watching is our sun producing incredible amounts of energy through the fusion of hydrogen into helium. If we could recreate this process on Earth, it would solve our energy crisis. A new source of power without the greenhouse gases. If we get this right, just 1 gram of hydrogen could generate the same amount of energy as the petrol it would take to fill this swimming pool. That's 100,000 litres. Impressive stuff. So why aren't we getting our energy from nuclear fusion? is, it's incredibly difficult. For fusion to happen, positively charged hydrogen nuclei have to get together. Now the problem with that is positive things just don't like each other. If you've ever played with magnets, you'll know what I mean. The like poles repel each other, and no matter how hard I try, I can't do it. And that's why fusion's so hard. I want to find out how the hydrogen nuclei overcome this repulsion. So, in the name of science, I've got a date with a plasma physicist, Dr. Melanie Windridge, at the circus. I'll be playing the part of a hydrogen nucleus, dressed in some rather fetching lycra. Sorry. Hi, Melanie.
Hello.
Great to see you here. Excuse me.
Okay.
Sorry.
Okay.
Now, here's the thing. I am a bit confused. Well, okay, I'm the centre of a hydrogen atom, a positively charged nucleus.
Yeah. And so's he.
Hello there!
Hello!
To be honest, I actually find him a bit repulsive. Well, a little bit. And if that's how all the hydrogen in the sun feels, then how does fusion happen?
Well, it's all about energy. If the hydrogen atoms don't have enough, then, well, you'll see what happens. Do you want to give it a try?
Do I have a choice? What I do in the name of science. Fusion failure!
Well, that's because you don't have enough energy.
Oh, does that mean I have to come back up?
Yeah, come back up, Fusion Boy.
Man, to be attractive to my mate over there, I'd need to be really hot. About 153 million degrees centigrade, which in circus terms is frighteningly high. If you think grabbing an acrobat looked tricky, you should try getting nuclear fusion to happen for real. It's not just the heat that's the problem, it's containing the reaction. On the sun it's done by gravity. On Earth they do it with magnets in places like this. JET is the biggest fusion experiment in the world. Inside here, incredible magnets constrain a donut-shaped hydrogen plasma 10 times hotter than the sun, giving it enough energy to fuse. That makes this the hottest place in Oxfordshire and the entire solar system. One of the people making fusion happen here is Dr. Maximus Salas. Wow. So this is the sort of mission control.
Exactly.
It's pretty impressive. So you can actually see what a fusion reaction looks like.
Yes, of course, you can watch it in this screen.
What we're seeing is impurities glowing. The actual hydrogen plasma has a similar wavelength to X-rays, so it's invisible to our eyes. It's amazing. And how much hydrogen is actually in that?
Oh, there's very little. If you actually could weigh the quantity in there, it would weigh less than a postage stamp.
It might be hotter than the sun in there, but I can't resist getting a closer look. Sadly, Maximus was worried we might vaporize, so the closest I got was inside this mock-up.
Plasma is exactly here.
What I really want to know is why, if they've made fusion happen, we aren't all powering our homes on the stuff.
About here, I would guess, would be the center of the plasma.
How much power have you generated?
Well, the maximum power we have generated is 16 megawatts, and this is a world record.
16, so that's 16 million watts.
Yes.
In terms of sort of, kettles boiling, or something,
I would say it's enough to boil around 5,000 kettles.
That's pretty good. That's pretty good.
No, it's quite good.
And how much energy did you have to sort of put in to get that energy
Well,
out?
that's the problem, you see. In order to get these 16 megawatts of power, we had to actually put in more energy than we took out.
But presumably the goal obviously is to put in less energy than you
Exactly. This is the aim of fusion, really, to be able to take out much more energy than we're actually putting in.
Do you think fusion is going to solve our energy problems? Can we do away with fossil fuels, for example?
Well, I think if we are successful in what we are trying to do here, then yes, fusion will solve all our energy problems.
Scientists predict it'll be at least 30 to 40 years before nuclear fusion is powering our homes. But if it means we have a cleaner source of endless energy, it's a day worth waiting for. Trying to control a superheated plasma is a problem I've got too. Let's get back to the hybrid rocket. Earlier on, I managed to build a rocket bike made entirely of high street components. But now, I'm going for the big one. A toffee, peanut and aluminium powered rocket. 10 times as powerful. Now we could have launched this rocket vertically, but that's not the traditional way of testing these things. So we've built this. A rocket sled. It's even been made to satisfy the stringent demands of Her Majesty's Rail Inspectorate, which is good. What's not so good is we've only got 200 metres of track to test it on. And worse still, 30 feet over there is a main network rail line. So we've chucked a few brakes on it. We've got brakes on the wheels, we've got a parachute, and if all else fails, we've even got a hook here that picks up a large length of heavy chain. On the bike, I was kind of worried for me. This time, I'm concerned for the whole of the home counties. Let's go. The key is getting the gas flow into the toffee tube just right, hence the last minute tweaks to the plumbing. This is it. 7 kilos of nitrous oxide. 4-foot long tube stuffed with toffee and peanuts. And this fire button. When I press it, it goes off. First, the toffee is lit with a standard pyrotechnic. Then I hit the gas button. 3, 2, 1... That was absolutely awesome. Approaching 200 miles an hour, the parachute didn't stand a chance. Nor did the brakes or the chain pickup. Luckily, the buffers kind of held. That is unreal. It's an actual train wreck. Every single braking system got ripped apart. The rocket failed to shut down. The only thing that stopped a major disaster was 1.5 tons of water. Well, now you know how a hybrid rocket works. From the supermarket to outer space.
200 miles an hour. That is some serious speed, Jem.
Not bad for a stick of rocks, seriously.
Indeed. Shall we say goodbye?
Goodbye.
See ya.
Bye.